Hello guys, my name is Gaurav Mehta and today I will be talking about declarative recursive computation on an RDBMS. Introduction. Modern machine learning platforms such as TensorFlow have primarily been designed to support data parallelism, where a set of almost identical computations are executed in parallel over a set of computational units. Now the challenges faced for adapting RDBMS technology for machine learning. However, there are a couple of reasons for a modern database system to not be able to be used out of the box as a platform for most large-scale machine learning algorithms. Crucially, such systems lack sufficient support for recursion. In deep learning, it is necessary to loop through the layers of deep neural networks and then loop backwards through the network to propagate errors. Now, parallelism in machine learning. Because one of the key benefits of machine learning on an RDBMS is automated parallelism, we begin with a brief review about parallelism in machine learning. In the general case, when solving a machine learning problem, we are going to given a data set T with element Tj, and the goal is to learn a d-dimensional vector of a model parameters that minimizes the loss function of the form. To end this, learning algorithms such as gradient descent perform a simple update repeatedly until convergence. Here f is the update function. Each update marks the end of the processing approach. Many learning algorithms are decomposable. That is, if t has a element tj, the algorithm can be written as the following. Now let us know about deep learning in RDBMS. There are two types of deep learning, simple deep learning and a mixed declarative approach for deep learning. A deep learning neural network is a differentiable nonlinear function typically conceptualized as a directed graph. Each node in the graph, often called as neurons, computes a continuous activation function over its input. One of the simplest and the most commonly used artificial neural network is a so-called fed-forward neural network. Neurons are organized in layers. Neurons are one layer of one in one layer are connected only to neurons in the next layer. Hence the name is feed forward. A mixed declarative approach. Perhaps surprisingly, a model parallel version of the algorithm is possible on top of an RDBMS. We assume that RDBMS has been slightly augmented to handle matrix and the vector data types, and assume that various matrix and vectors have been chunked. Now, using recursive SQL, there are two ways to use recursive SQL: forward pass and backward pass. Here are the examples of forward pass. We create a table A and select two columns, column and value of that column. Now from the data input, we then send the activation across the links in the network. Here you can see how we send the SQL code of how we send the activation across the links. Those links are then used to compute subsequent activations and finally used to perform the prediction. Backward pass, for example, at subsequent layers the error is identified. Now we use the errors to update the weights and the bases. We now have a finally declarative implement of neural network learning. Executing recursive plans. There are three ways to execute a recursive plan: frame-based execution, heuristic versus full unrolling, or planned rolling. Now, frame-based execution, our idea for compiling and executing computations written recursively in this fashion is to first compile the recursive computation into a single monolithic relational algebra DAG, and then partition the computation into frames or subplans. In heuristic and full unrolling, one could imagine two alternatives for implementing a frame-based strategy. The first is to rely on heuristic, such as choosing the outermost loop index, breaking the computation into frames using the index, and so on. This method has a lot of problems. So instead we opt for an approach that performs a full unrolling of the recursive computation and turns it into a single monolithic computation. And then we define an optimization problem that attempts to split the computation into frames so as to minimize the likelihood of materializing a large scale number of tables. Plan rolling. Our unrolling algorithms attempts to leverage an existing database query compiler to transform an SQL query into an unoptimized relational algebra plan. At a high level, the algorithm recursively chases the original query's dependency. Whenever a dependency is found, a lookup table is checked to see if the dependence has previously been compiled. If not, the recursive dependency is expanded. Now, the experiment details. In all our experiments, all implementation run the same algorithm over the same data. Thus, a configuration that runs each iteration 50 times faster than original configuration will reach a given target loss value, that is 50% faster. Hence, rather than reporting loss values, we report per iteration running times. All implementations are fully synchronous. For an apples to apples comparison, we choose synchronous learning as there is a strong evidence that synchronous learning for large dense problem is most efficient choice. There are two sets of FFNN experiments. In the first set, EC2 R5D 2x large CPU machines with 8 cores and 64 GBs of RAM were used. In the second set, at various cost levels, we choose set of machines to achieve the different performance. For TensorFlow, this 829 was released by GPU machines, CPU for parameters. For SimSQL, both CPU and GPU machines achieved similar performances. Word2Vec and LDA were run on clusters of Amazon EC2 M2 4x large CPU machines, each with 8 cores and 68 GB of RAM. GPUs were not used as they are ineffective for these problems. LDA are not neural learning problems, and word2vec running time on TensorFlow is dominated by parameter server request rather than computation. Now the results. We begin with examining the utilities of cutting algorithms. Using 10 CPU machines, we run FFNN learning. 40,000 hidden neurons, batch size 10,000. W2V learning and LDA using three different cutting algorithms. The experiment is simply greedy version of GQAP solver. Second, we use the full solver rather than taking a probabilistic view of the problem. We apply the idea of simply reducing the number of edges across the frames, as this corresponding to the table that must be materialized. We call this the cutter as it treats all edges as being equivalent. Finally, we evaluate the full algorithm using the cost model. We report the per iteration running time for various options. Now the figure 6 shows per iteration runtime using frames from various cutting algorithms: fully optimized cutter, min cutter, min cut cutter, and greedy cutter. Greedy cutter fails for FFNN graph cutting algorithm and is the worst amongst all of them. Now these are some of the results where we compare frame based versus monolithic plan execution time. The frame based is absolutely better because it is just 12 seconds and 53 milliseconds per iteration time. Then we see per iteration running time for word2vec. The time is in parents for an RDBMS is the time required to execute a code that generates each batch. Now RDBMS is obviously a better version, but TensorFlow fails for larger computations. Now average iteration time for FFNN learning maximizing performance at a specific dollar cost. Here is a summarized version of it. Thank you.